We are looking at organic chemistry series, and today we are looking at isomerism. Isomerism is an interesting topic in organic chemistry. But what do we mean by isomerism? First of all, isomerism is the existence. You should know that, or in other words, you can say an occurrence of organic compounds or compounds with the same molecular formula. So they have, let me just, one same molecular formula, and then but they exhibit or possess different, it can be either different structural formula. If it's not different structural formula, then it can also be different physical and or chemical properties. Chemical properties. So that is the simple definition that we can give for isomerism. Now, as isomerism is a broad topic, it's divided into two. We have two types of isomerism. The first one is structural isomerism. Structural isomerism. One. And then two is stereoisomerism. Stereoisomerism. Structural isomerism can also be called constitutional isomerism. So you can put that down for your read, just in case you come across it in any book. Structural isomerism is also known as constitutional isomerism. Now, let's define structural isomerism. Now, for structural isomerism is the existence of organic compounds with the same molecular formula, but different structural formula. Now, under this class, we have three main types of structural isomerism. The first one is chain isomerism or open chain isomerism, which can also be called, you remember from our previous video where we said that an open chain is a straight or branch chain. So it can also be called straight and branch chain isomerism. Okay, straight and branch isomerism or chain and branch isomerism. Now, under this compound, the simple definition I can give for this is that they have the same, so we are not different from the original explanation. They have the same molecular formula, but different ways in which the carbon atoms are linked to each other. Okay, so different ways, they have different ways in which the carbon atoms are linked to each other. And let me just give you an example to clarify the whole situation. Example. Now, imagine a compound with 5 carbon atoms and then 12 hydrogen atoms. Okay. Now, this compound can be represented this way in a straight chain format where you have hydrogen bonding here. So this is pentane or 1 pentane. Now this same compound can also be represented this way where you have another CH3 here. So you still have your 12 carbon atoms, because if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the 3 here, 12. Okay, this is 2-methyl butane. 2-methyl butane. In that same way, you can also have a compound like C. Okay, so that is that for now. Just to save time. Okay. Yes. So that is structural, a type of structural isomerism known as chain isomerism. The second thing that we can talk of is positional isomerism. Positional isomerism. So the definition does not differ so much from the original definition. It is the existence of organic compounds with the same molecular formula, right? But different positioning. So they have different positioning of their substituents or functional group. So different positioning of their substituent or functional groups. We will take time and then talk about substituents and functional group. Okay, but let me just give you an example. This compound CH3, when you see any compound like this, just CH3, this can be a substituent. You can have CH2, CH3. This is also a substituent. Functional group, an example is the alkanoic acid group. We have an OH group. These are functional groups, so know the difference. Now, let me give you an example of a compound with carbon atoms 5, 11 hydrogens, and then an O. Okay, so we want to look at positional isomerism occurring in a compound like this. Now let's draw the structure and see. 1, 2, 3, 4, 5. 5 carbon atoms. Now, so we can bring our H's here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then, because we have, what do we call it? So because we have this, we can bring the OH here, and then we'll have our atoms here. Now look at something very careful. This is a pentanol, right? One pentanol. Now if you look at another example this way, you can also have 1, 2, 3, 4, 5. But this time this OH group will be here. And then you have your carbon atoms, right? Good. Because I already said that these ones are functional groups. And so if you have something like this, and then the carbon is here. Now look at the name. This becomes 3-pentanol. So it is exhibiting positional isomerism. The position of the functional group has changed. Okay, has changed. In that same way, you can also have different substituent changing position, and that qualifies them to be called positional isomers. So 3-pentanol is a positional isomer to 1-pentanol. You understand? Yes. And then the last group of structural isomerism or structural isomers is functional group isomerism. So we have functional group isomerism. Functional group isomerism. Simple definition. It doesn't differ so much from the general definition. These they have the same molecular formula, just that this type of isomerism occurs between different functional groups, and it is exhibited in nature. So anytime you have an alkanoic acid, and I told you that we'll go into the nomenclature of these compounds. Okay, so don't worry so much. We have a functional group known as alkanoic acid group, and then we also have esters. Esters are alkanoids. esters are alkyl-alkanate. They always exhibit functional group and isomerism. Now let me give you an example. Imagine you have a compound like CH3, CH2, COOH. Now this is propanoic acid. Let's look at something here. When you have CH3, COO, and then CH3. Yes, when you have a compound like this. Now, you realize that this is propanoic acid. This is what? This is ethanoic acid. So ethanoic acid. Ethanoic acid. Now let's count the number of hydrogen atoms here. There are 6, carbon atoms are 3, oxygen atoms are 2. If you look here, 5, 6 hydrogen atoms, 3 carbon atoms, and 2 oxygen atoms. And this qualifies it to be a functional group isomerism. Functional group isomerism does not only occur between alkanoic acid and then alkyl-alkanate. It also exists between alkanes, and then alkenes and then cycloalkanes. Right? And you know that we said in our previous video that cyclo qualifies it to be what? An alicyclic compound. And then alkenes is also a functional group. We will go into them later on. But let's look at an example. If you have a compound containing containing 4 hydrogen atoms and then 10 hydrogen molecules. Now let's draw the structure for alkane. An alkane will be 1, 2, 3, and then you have your hydrogens here. Okay, so you have H. Don't forget that there is an unsaturation here, a double bond. Now if you count, let's count the number of carbon atoms here. I have hydrogen atoms, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They are 10. Now, let's draw the structure for cycloalkane. Okay, we have a carbon here, so this carbon is bonded to 2 hydrogen, and 2 hydrogen. Because already it is also connecting, this carbon is connecting to the carbon here and carbon here. And we know that carbons are tetravalent, so they can connect only 4. So 1, if the carbon is here, it is connecting with the carbon here, which is 1. Another carbon here 2, and then 2 hydrogen. So realize that you just use only 10 hydrogens here, and then you form the same compound with an unsaturation. But this one is an aliphatic compound, and then this one is an alicyclic compound. So that is the difference. Functional group isomerism happens with different molecules. Even an example is an alkoxy group and then an alkanol. There exists functional group isomerism between them. Now let's hop on to stereoisomerism. Stereoisomerism. Now, under stereoisomerism is the existence of organic compounds, this time with the same molecular formula and structural formula. So they have the same molecular and then structural formula. But they can possess different spatial arrangements. They can have different spatial arrangements or different physical properties. been using different physical properties, but we don't really explain them. Now, example of physical properties that may differ is their boiling point, their solubility, their refractive index, melting point. These are all different physical properties that can be affected. And we've realized that even with zero isomers, yes, they have the same formula, they have everything, but their physical properties actually cause us to probe into their research. And under zero isomerism, we have three types. We have three types of zero isomers. So two types of zero isomerism. So two types. We have optical isomerism, and then we have geometric isomerism. Now, first of all, let me start with optical isomerism. These compounds, they have different structure, right? Different structural and then molecular formula, but they have different arrangement of substituent. So they have different arrangement of substituent. So substituent. Let's say A, B, C, and then D. They have different arrangement of their substituents. Now, let's go deeper. Let's dive deeper into the types of optical isomerism. And optical isomerism, we have what we call enantiomerism. So we have enantiomers or enantiomerism, and then two, we have diastereomerism or diastereomers, and then enantiomers. Even under diastereomers, we would also learn we have something called epimers. Okay? Yes, epimers. But our focus and then our description of epimers will be treated when we are learning about polymers, where we will learn about the nutrients, carbohydrates, proteins. That is where we will learn epimerism. Now, enantiomers. These are non-superimposable mirror images. And the example that you find in every book is your hand. You see, your hands are mirror images of each other. But when you want to superimpose, because they are mirror images, if they are all facing up like this, you don't change their position so that they face together. No, they are all facing. You are looking at my palms right now. So if I bring them this way, you see that they don't superimpose. My thumb is to the right, and then the other thumb is to the left. So they are non-superimposable, even though they are mirror images. That is the same thing with enantiomers or enantiomerism. So the existence of organic molecules with the same molecular and structural formula, but they are mirror images and non-superimposable. Okay, so that is the simple definition. And this is it's because of their spatial arrangement. Yes, and then we have, so an example, you can do a carbon atom 2, 3, 4. So 4 carbon atoms. So this compound is actually 2 butanol, right? 2 butanol. Now, you see it is exhibiting enantiomerism, okay? With the fact that it has different substituents, different functional groups. So if we draw this same compound, CH3, then we bring the we bring the CH2, CH3 here, and then an OH here. We've changed positioning spatially because you can't really see it, it's not defined here, but spatially their positions have changed. You have your ethyl substituent to your right, to your left, and here is to your right. So different enantiomerism. And once again, these are spatial arrangements, so you won't really recognize them in this description. And then epimerism, we will treat them under biological chemistry when we are talking about the polymer molecules, the nutrients. Good. Now let's look at geometric isomerism. Now for geometric isomerism, once again, we have same molecular and then structural formula. The existence of organic molecule with the same molecular and then structural formula. Structural formula, but they have different spatial arrangements. They have different spatial arrangements. Different spatial arrangements. Due to the restricted rotation. So they have restricted rotation at the carbon double bonds. So anytime you have a restricted rotation at a carbon double bond, then you have geometric isomerism. Now let me give you an example. If you have a compound C to C with let's say substituents A, B, and then C. Another compound C to C with substituents A, B, and C. And then we have a third compound with C and C, A, B, and C. Now, realize that AA, C, and B qualify to be a geometric isomer. This compound here, A and then A, on this axis also qualify to be a geometric isomer. But this compound, we don't know what it is because there is no restricted rotation. And for this, a compound like this, which lie on the same plane, this compound is known as a cis isomer. A cis isomer. And then a compound with molecules on this axis are known as trans isomers. Okay? So anytime you see a compound like this, then it doesn't become a geometric isomer because we can't see the restricted rotation. Okay? Yes. Now we would look at the nomenclature, but the cis and then the trans isomerism and the geometric isomerism kind of have ambiguities when it comes to their nomenclature, and so we are adopting new structures or new naming patterns with what we call the antigens, and then the zoosamines, which we will look at. So Z and then E. Okay, we will look at these two in our later videos. Okay, when we are doing nomenclature of organic compound. So thank you very much for watching our videos. Don't forget to subscribe.